we want to answer the question, when is the total complex exact? So here the word exact has the same meaning as it has in a complex. So that is the kernel is equal to the image. So the answer is when either the rows or the columns of the total complex are exact. So if the rows are exact or if the columns are exact, then the total complex is exact. So that means if the total complex is exact, its homology groups are going to be 0. So obviously we can make an analogous argument for cohomology groups. So how would we show this? So what is the exact statement we need to prove? So we will just do the proof for columns, and you can just copy that proof for rows. So because either rows or columns we have to show. So we focus on columns. So consider the columns. So if the columns are exact, we need to show this. So say M is the element of an entire diagonal. So you know that the total complex lives in the entire diagonal. So if M is the element of the entire diagonal, so these are the elements of the entire diagonal, you can see the indices add up to I. So I minus 1 plus 1 is I. So this M, an element, this is of this form. So it is M0 here, it has I coordinates, M1 lies in here, then M2 so on, and then Mi lies in here. So if M has this form such that you take its total differential, if its total differential is 0, so obviously total differential will have two parts. It will have the vertical differential d and the horizontal differential delta. So if this M lies in the kernel, then M also lies in the image of some previous one. So therefore then so this M has to be equal to d of something else, where n lies in the I plus 1 entire diagonal. So n is of this form. So you start with n of 0, then you have n of 1 all the way to n of I plus 1. So n is this big tuple here. So this is n, and m is this big tuple here, m0, m1, m2 all the way to mi. So we are saying that kernel will be contained within the image, and we have already seen that this total complex is a complex, so kernel already contains the image. So this has been shown before, because that is how this becomes a complex. Now we are saying this statement should hold. So if this holds, then you have equality kernel is equal to image, and then you have the exactness of the total complex. So to prove this case, we will just take a specific instance, and inductively you can show for I cases. So what we are going to do is we are going to take M lying in I equals to 2. That is, we are going to take M lying in this anti-diagonal, and then we are going to lift it to this anti-diagonal here. So let us see this. So this will be an inductive process, so you can keep on going on and on. So we are going to inductively lift up the elements from one anti-diagonal to another. So we have to show this exactness of the total complex. So let the differential of the total complex be d. So you start with a simple case of I equals to 2. So this entire diagonal is where we start with, and you pick up an element m in this entire diagonal which lies in the kernel of our differential, and you have three elements in m, m0, m1 and m2. So m0 lives right here, m1 is here, and m2 is here. So the first thing is that this m is in the kernel of d. So kernel of d means you have to apply this map. This will be the 0 and this will be 0. So let us see this. So this m1 via this map d gets mapped to d of m1, and this m0 gets mapped to delta m0. So this lies in the kernel of our differential. So this is 0. So our definition of differential is that you have to apply the horizontal differential, which is delta, and the vertical differential, which is d. So this is first map. Here this goes to 0, so that's why we are not applying this here. So now this m1 via this map delta will get mapped to delta m1 here, and this m2 via d will get mapped to d of m2. So you have d of m2. Again this will be 0, because we are saying our first element lies in the kernel of D. So we get these two equations. dm2 plus delta m1 is 0 right here, and this one dm1 plus delta m0 right here. So again there is a horizontal map right here with 0 here. We are ignoring it because it just goes to 0. So now we got to lift this to an element of this entire diagonal. So this entire diagonal had sum as 2. 2 plus 0 is 2. 1 plus 1 is 2. Here it is 3. So we got to lift this up, and inductively we can lift it to any number of steps. So the first thing is we set here n0 as 0. So this is our choice. This is not going to do any harm. So this column is exact. So we are saying the columns are exact. Columns are exact. So this is what we are assuming to start with. Columns are exact. So this column is exact. So this map is therefore surjective. You are able to lift this m0 to some element, say n1 right here. So first we set this n0 is 0. That's what I'm writing here. And in the second column it is exact. So you make an n1 and m2 one such that d of n1 is m0. So you apply d to this map, you get m0. Now you see anti-commutativity. So if for anti-commutativity, so first to n1 you apply delta and then d, you land here. So first you apply delta and then d, you land here. And if you go the other way, you first apply d and then delta. So first apply d and then delta, and you put a negative sign. So this comes from anti-commutativity. But this d of n1 you have set as m0. So instead of d of n1 you write m0. Now this part comes from here, this equation. So d of m1 is equal to minus delta m0. So this we are getting from right here. So what does this lead us to? Now focus on this and this. So this gives us, both have map d there. So m1 minus delta n1 will lie in the kernel of D, because dm1 minus d of delta n1 is 0. So m1 minus delta n1 lies in the kernel of D. So where is this element sitting? So this m1 is right here, and you apply delta n1 to it. So this is where this element is sitting. Now this is exact. Now since this is exact, we can lift this up. So you can lift this up. So this you can lift up to, say this lies in kernel of D, so you can lift it up to say an element n2 here. So n2 you apply d to it, you get m1 minus delta n1. So d of n2 is m1 minus delta n1. You can do this because this column 1 is exact. So the first column is exact, so you can do it. Now you can rewrite m1 as, bring this on the other side, so delta n1 plus d n2. So again you use anti-commutativity. Now for element n2, first apply delta and then d. First apply delta and then d for n2 is same as first you apply d and then delta. So first you apply d and then delta, and anti-commutativity means you put a negative sign. So you get this. But now you already know this d of n2 is m1 minus delta n1. So you plug this in here, you expand it out, and you know that delta square is 0 because delta is a chain complex. It might not be exact, but it is a chain complex, so delta square would be 0. So you just get minus delta m1 is equal to d of m2. Now this comes from this part here, because now you can see minus delta m1 is equal to d of m2. Now you just focus on this part, d of m2 and d of delta n2. So d of m2 minus d of delta n2 is 0, because you have equality here. So m2 minus delta n2 lies in the kernel of D. So m2 minus delta n2 lies in the kernel of D. So since it lies in the kernel of D, you can again lift this up to some element n3 here. So we can lift it to some element n3 here in m03 such that d of n3, you apply d to it, you get here. And you can rewrite m2 as dn3 plus delta n2. So just bringing delta n2 to the other side. Now let us check that we have properly lifted it up. So we have been able to lift this m0, m1 m2 to these elements n0 n1 n2 n3. So we have to check this. So we are saying that we have been, this is n0 n1 n2 n3. We should apply d to it and should get m0 m1 and m2, because we first said that these elements get mapped to 0 from here. So you are able to lift it up. So let us see this. So you apply d of n. So d of n, if you apply, you first start with delta n0. So to n0 you apply delta, you don't apply d here because it gets mapped to 0 right here, so you skip that part. So delta n0, you land here, but we are saying n0 is just 0, so this we chose as 0, so this becomes 0 right here. Now to n1 you have both the maps d and delta, so you have to apply both the maps to n1, d as well as delta. So dn1 plus delta n1, so dn1 plus delta n1. But you already know that this d of n1 is m of 0. D of n1 is m of 0 right here. So you get this. Then to n2 you have to apply both maps d and delta again, because both maps are going here, none of them are going to 0. So you get d of n2 plus delta n2. Now you can see that this m1 is delta n1 plus d of n2. So delta n1 plus d of n2. So this is your m2. And for the last map n3, you apply d2 here, it lands here. You apply delta to it, it lands to 0. So you don't worry about delta. So just write d of n3. But again, our definition of m2 is d of n3 plus delta n2. So d of n3 plus delta n2. So this, you can see it here, is m2. So you apply d to n, you get m0 m1 and m2, m0 m1 and m2. So we have been able to lift. So this is just an inductive procedure. So you start with the first element, lift it, use anti-commutativity, get something like this, lift it, use anti-commutativity, get this, lift it. So you can use it for going from like case I, you can lift it to I plus 1. Just like from here, this sums up to 2, we have been able to lift it to this part, which sums up to 3. From 2 to 3.